So as we kind of wrap up our discussion about SN1 and SN2 reactions, we've kind of gotten along this idea that sometimes you can have some competition where a reaction might go SN1 or SN2. So what are some conditions that are really going to help push it in one direction or the other? The first one is going to be thinking of our substrate. And your substrate is going to be your kind of R leaving group. Your SN1 are going to favor substrates that have high levels of other stuff around it. So we could describe that as our substitution. Secondary and tertiary are going to be our most common. In SN2, we really want to have very little sterics because we don't want to get in the way of our group coming to attack. So we really prefer things like methyl, primary, and secondary. You'll note both of these have secondary. Secondary can kind of become a little bit more of a shit show where it can kind of go any direction. Our next thing is going to be our solvent. For our SN1, we really want to have a polar protic. Protic meaning the ability to hydrogen bond, to interact with our reactive intermediates to help stabilize those. In SN2, we really want a polar aprotic, a solvent that does not hydrogen bond and is not going to get in the way. We do not want it to interact with our nucleophile. Speaking of our nucleophile, SN2 really wants to have a strong nucleophile. SN1 doesn't really matter. So if you're trying to promote an SN1, typically you would think about giving it a weaker nucleophile because you cannot get any SN2. The last thing that we talked about was the idea of your leaving group, and all of them need good leaving groups. So there's really kind of nothing to kind of add there other than a really quick reminder that alcohols are not good leaving groups. Let's go ahead and jump. So here's kind of a quick summary of a lot of things with our SN1s and our SN2s. This is all the way at the last page of our notes. SN2 reactions are concerted reactions. They happen all at the same time. Your nucleophile will come and attack your substrate, and then your leaving group will leave. This all happens at once, and you have two arrows in just a single step for your SN2 mechanism. Your SN1 mechanism is going to have two steps, each with just one arrow. The first is going to be your leaving group's going to leave to form your carbocation, and then your nucleophile will then come capture that carbocation to form your bond. Both of them are going to form your nucleophile plus substrate as your key product. The way they're going to get there is going to be a little bit different. Here's kind of another kind of quick summary table for your SN1s and your SN2s, and thinking about all the different things that we've kind of talked through with a bunch of the videos. Your SN1s generally are going to have weaker nucleophiles. Your nucleophile doesn't matter because it's not part of your rate determining step, which you can see all the way down there in kinetics. In your SN2, you need a very strong nucleophile, and often when we think of strong, we are often going to think about something that carries a negative charge. Again, when you think of your substrate, your SN1 wants a bunch of inductive effect, so it wants a bunch of things around it. So it wants a substrate that is tertiary or secondary, where your SN2 is going to prefer your primary or secondary. You could also have methyl, but then it's just methyl and there's nothing else. You don't see that too often. Primary is a lot more common. When it comes for your solvent, your SN1 really needs a good solvent that can ionize or stabilize your reactive intermediate. These are going to be your protic solvents. Things like your alcohols or your waters, that can hydrogen bond, are very common. SN2, if it is non-charged for your nucleophile, doesn't matter as long as it's polar, it's good. Typically, you'll generally prefer your aprotic solvents because your aprotic solvents are not going to get in the way of your nucleophile. Leaving groups, they both want good leaving groups. Common examples of good leaving groups are going to be things like your halogens. Things like your iodide and your bromine are going to be really good. Chlorine's okay. Fluorine kind of sucks. But it doesn't suck as bad as alcohol. Alcohols are really bad leaving groups, and there's two ways you can make an alcohol into a better leaving group. You can add acid to turn it into an oxonium, or you can do a reaction to turn it into a mesyl or a tosyl. When we think of kinetics, your SN1 is a first order reaction, so we can write the rate of the reaction is equal to a rate constant times the concentration of our substrate. Our nucleophile is not involved at all. In an SN2, we have a second order reaction where the rate of the reaction is equal to our rate constant times our nucleophile and substrate concentrations. When it comes to stereochemistry, SN1s form racemic mixtures. Your reactive intermediate of your carbocation is an sp2 planarized substrate, so it does not have any stereochemistry defined at that point. So your nucleophile can attack from either direction and will form both your R and S. So overall, you're left with a racemic mixture. In your SN2, you get a backside attack, which involves an inversion of your configuration. So therefore, you're going to change your stereochemistry at your site of attack. You don't change all of your stereochemistry. If there's a group that's way far away from your point of attack, that's not going to change because it's not involved in the actual inversion of configuration. Finally, in SN1s, there are chances to do rearrangements. We showed rearrangements through both resonance and a hydride shift. Those occur because you have a reactive intermediate that can undergo some transformations. In SN2, everything is concerted, it all happens at once, so you don't get any rearrangements. It is impossible. And there's kind of a quick snapshot in, looks like less than 7 minutes, about your key comparison between your SN1s and your SN2s. We'll go ahead and wrap up there and see you in the next one.